Good afternoon. Welcome everybody in the classroom. Welcome all those who are joining us remotely. This is the MARESUNEX Seminar, and my name is Dr. Peter Mullner. I lead this event together with Dr. Steve Crowley and Dr. Richard Lambert, and it's our pleasure to welcome Richard Lambert as our guest speaker. Before I introduce him, I would like to quickly give the rundown of our afternoon. So that everybody also joining remotely knows what we're doing. So after the introduction, Mr. Lambert will give his presentation and for 40 minutes. Then we'll have a little break, and us here in the room and those remotely who want can join a discussion group for 5 minutes where we will talk and discuss the prompts that Mr. Lambert has provided. And those remotely might also just stay in the main room and then join the discussion or Q&A after that. All right, with that, it's my great pleasure to introduce Richard Lambert. Mr. Lambert retired from SLR International Corporation in 2023, to which he and 4 partners sold Roscoe Postal Associates, RPA, in 2019. Mr. Lambert was president of RPA USA and Chief Operation Officer of RPA since 2011. Mr. Lambert is a senior mining executive with more than 40 years experience in all aspects of mining development from permitting to closure. He was employed by Fortune 500 mining companies for the first 17 years of his career. Since then, he has been providing mining contracting and consulting services. Mr. Lambert holds a bachelor's degree in mining engineering from McKee School of Mines at the University of Nevada, Reno, and an MBA from Boise State University. So go Broncos, and welcome our graduate back here into this classroom. He is a registered professional engineer in the states of Wyoming, Montana, Idaho, and the province of Ontario. He was an adjunct professor at the University of Toronto, where he taught a course on mineral reserve and mineral resource estimation. As a consultant, Mr. Lambert has been involved with over 250 mining properties around the world and has been on site at over 120 mining properties. He has been on all continents, including the Antarctica, as we just learned a couple of minutes ago. And if I were to continue here what all his experience were, the hour would be passed very quickly. So I stop here and hand it over. Please help me welcome Mr. Lambert. It's better probably on that side, isn't it? Better. Okay. That's great. Okay.
Everybody's here. Okay, thanks. Just tell you a little bit. So as you know, I went to school here at BSU, but I got my master's here. I worked for Morrison Knudsen downtown here for 7 years. And I worked up at the Delamar mine up by Jordan Valley for 8 years. And currently I'm retired, but I'm still doing project finance work, reviewing projects for the banks as their technical expert. And I'm currently on the Stibnite mine. We're the lender's technical agent. So I think we covered the rest of this. Some of the projects currently working on, I'm doing Reko Dig in Pakistan for the lenders, doing Stibnite, as mentioned, and doing Nueva Centinela down in Chile as well. So the goal here is just kind of give you some mining basics, and we'll go through some terminology, and then we'll discuss some mining methods, discuss a little bit about mineral processing, and then try to go through the mining life cycle, the stages of a mining project, and some of the valuation of a mine and how the value increases over time. And then talk about some opportunities and questions and answers. Okay, so some basic terminology, and this is a picture that shows an open pit mine. And after the open pit, after you've extracted what you can economically, then it goes underground. In this case, we have a shaft that goes on the side here. You have a drift or a crosscut that then goes across to access the property, the ore body. And then you go in and you mine that area out using underground methods after the open pit methods have been exhausted. Just some of the key terms here. The mined out area there is typically called a stope. We have a crown pillar, which is a piece of ore that's left at the bottom of the pit, and that's to protect the underground workings. It's basically a crown pillar is a cap that keeps the ground stable. All right. So on the open pit side, open pit mining is the most economic. It gives you economies of scale, bulk mining, large scale, usually lower grade than the underground mines, larger equipment, up to 400-ton trucks, which is actually pretty impressive when you see them. The startup capital can be high for the equipment and the process plant and things like that, but it's lower than doing the same thing underground, because usually underground requires more infrastructure and more work to be done at a higher cost. Unit operating costs for open pit mining are between $1.50 and $4 a ton. And then the strip ratio is the ratio of waste to ore. That's how much waste you have to move to get 1 ton of ore. And typically you like to see a lower strip ratio in the 2 to 4 range. And that's what most copper mines and things like that will be. But other projects like gold mines, you can see strip ratio as high as 10 to 15 to 1, depending on the value of the metal and the grade. So some of the open pit mining, basically the unit operations, you start with drilling and blasting, as you can see up in this picture on the left. You drill the hole, you load it with explosives, typically ammonium nitrate, and you blast it, you break the rock, and then you load it with the shovels like this one here, the white one. You load it into the trucks haul it out of the pit and to the process plant or to the waste dump. So this is one of the 400-ton trucks. You can see the man standing next to it reaches up halfway up the axle. Those trucks sell for $7 million each. They're pretty impressive pieces of equipment, especially with the technology nowadays, and the automation that a lot of mines are putting in is very impressive. Underground trucks, we got this orange one here. This shows an underground truck. That's a 60-ton truck, lower profile, so you can work in lower headings and not hit the roof rack or anything like that off the back of the truck. And then highway trucks, you see a lot of these like in gravel and small scale mining situations, like a truck and a pup like this one here. Some of the open pit mining terminology, you have a ramp, which is where your haul trucks come in and out. You have the pit slope that goes from crust to toe. That's the slope angle. And the slope angle is determined by geotechnical metrics. You got to understand all the geotechnical aspects, how strong the rock is, how well it stands up, to be able to design the proper slope. You'd like to make them as steep as you can, but you don't want them to fail because of safety concerns. The bench it's mined on benches. Typically in large mines, we see 50-foot benches with large electric shovels. And then the berm is the catch bench at the bottom of the bench, basically catch any falling rock to keep you from rolling down the hill and hitting some other equipment. The stripping ratio, as I mentioned, is the ratio of waste to ore. In this picture, the yellow is the waste and the red is the ore. As you go deeper, the stripping ratio typically increases. And as that increases, so do your costs. So you got to watch, and you can only go so deep sometimes because the costs start to offset the cost of going underground. This is the Escondida mine in Chile. It opened in 1990. They're moving 1 million tons a day from this mine. It produces 6% of the world's copper, one mine in Chile. It's pretty impressive. Bingham Canyon mine in Salt Lake City. It's the largest man-made excavation, 2.5 miles in diameter, 4,000 feet deep. I actually worked there for a year back in the 80s. It's a large copper mine with some gold and silver credits as well as molybdenum. So they get value not only from the copper, but from some of the other metals as well. This is a Chuquicamata mine in Chile. It started in 1915. This was actually originally owned by an American company, and then it got nationalized in Chile back in the 70s and became part of a company called Codelco, which is a Chilean mining company. It's very similar size to the Bingham Canyon in Salt Lake. They've hit the bottom of the pit in terms of economics now. So they're going underground and they're going to do a block cave, which is going to let all this material cave in, and they'll recover it from underground, chasing the ore body as it goes deeper. So that's kind of a quick synopsis of some of the open pit aspects. Talk a little bit about underground mining. It's got a higher unit cost, requires higher value ore, typically higher grades. The methods you choose for underground mining are very dependent on the shape of the ore body. If it's flat lying, you use one method. If it's steeply dipping, you use another method. But you have to evaluate all these things, and you got to look at the rock strength and understand what rock is going to hold up, because not only do you care about the ore you're mining, how well that stands up, but you care about the waste rock on the sides, if that's going to hold up as well. So that you need to understand all the geomechanics of the entire deposit to pick the proper mining method. Typically higher infrastructure capital, as I mentioned, the shafts, underground access, things like that. You know, to sink a shaft's $25 million. It's not a cheap thing to do. The costs range from $6 to $12 per ton of ore for room and pillar, up to $150 a ton for some of the smaller, more narrow vein mining methods that require much more mechanization and narrow cuts, and it just makes it more difficult for mining. Typical production rate from the underground mines is 1,000 to 10,000 tons a day. Deep mines are more expensive the deeper you go, because you get into other problems, not only with the depth of the mine and the length you have to haul, but also with water. You get more water, and you have to air condition. So actually, Carrier was one of the first guys to, Carrier air conditioner guys were one of the first guys to air condition a mine down in Brazil back in the 1930s. But it's very important as you get deep, because the temperature of the rock, you have to provide air conditioning as well. The deep mines prevent a lot of challenges, because the rocks, not only do you have the pressure and the strength of the rock itself that's a concern, but all the surrounding rock and the pressure from when you're 8,000-9,000 feet deep, the pressure, you get rock burst and other things that happen that you have to monitor. And it requires a lot of like phones and things like that down there, that you got to monitor all the noises and understand what's going on in the rocks. This is just a quick thing on underground mining methods going from block cave down to shrinkage. There's two arrows here. One, production increases with the ones on top here. So you have decreasing production as you go down, and you have increasing costs as you go down. But basically comparing different mining methods: block cave, induced cave, room and pillar, long hole, mechanized cut and fill, Lucky Fridays cut and fill, shrinkage, and things like that. Henderson Mine in Colorado is one of the largest block cave mines in the U.S. They're producing about 30,000 tons a day. So block caving, basically, the idea here is that you don't have to blast. You excavate a certain amount of rock from the bottom, and you let the rest just cave on itself, so that you're saving the cost of blasting, and you're not having to break that rock mechanically. It breaks itself. So this is very popular in the large copper mines and things like that. You get rates up to 160,000 tons a day. You have to allow for subsidence as well as for breakthrough through the surface. And then you got to look at your angles there as well in terms of stability for your draw points and the entire design of the draw points. This is the Andina mine in Chile. Between two open pit mines, there's a block cave, and you can see where the circle is here. That's where the cave goes into the ground. But that's what the impact is to the surface from the block cave. And they're drawing all this material out from underground and processing it underground as well. Room and pillar mining is typical for flat-lying deposits. We see this a lot in coal, potash, trona, salt mines. Rates of 2,000 and 20,000 tons a day. Typical extraction is 65 to 75%. You leave behind these pillars to maintain the roof and for support in the areas. So you have these, that's what makes it a room and pillars. The rooms are where you're working, and excavating the material, the pillars is what you leave behind. There's a cut and fill mining method. You can see there's a small load haul dump unit excavator. And basically you're working on the level here. You're filling beneath yourself and you're running on that surface so you can get up to the next level and drill that out and break that rock so you mine it. And then you continue doing that, bringing your fill in behind you and advancing going up. This is a little bit slower, 100 tons to 5,000 tons a day. It's used for narrow veins. It's very selective and fairly high cost. You're getting up closer to $80 to $100 a ton when you get up into these. Shrinkage stoping is similar to the cut and fill, except for you don't have the fill underneath. You're basically breaking the rock. You're letting the swell of the rock give you your working surface, and you're excavating just what you can each time to be able to still maintain that height for getting your drills and other equipment into there. It ties up a lot of inventory. So you don't really make money on these until you're done with that stope and you can draw out the entire stope. Typically you see rates of 500 to 2,000 tons a day. Very selective. It requires steeply dipping ore bodies, narrow vein. Then the most common underground method probably is long hole open stoping, which is basically going in and drilling out these rounds. As you see depicted here. It works best with near vertical mineralization. You need good wall rock. It's more productive. Basically, you're drawing everything out from the bottom as you break the rock, and you just continue to haul that out either by rail or by haul trucks. Vertical crater retreat is also another version of long hole stoping. You get 2,000 to 1,000 tons a day. You're taking these horizontal slices. It's a lower cost and more productive than some of the cut and fill and some of the other methods. Sublevel caving is actually another version where you're basically assisting because you still have to drill and blast. So unlike block caving, which caves by itself, you have to drill this material and break it to get it to come in. It's not as common. One of the big issues here is dilution, where you get waste rock coming in and contaminating your ore. So you got to be careful to make sure you don't have too much dilution. Another mining method is in situ mining, becoming more popular. We see it a lot in uranium, salts, bromine, a lot in sulfur, and also in copper now. So basically you're putting material into the ground, circulating it, and using extraction wells around it to recover that material. For copper, they use a sulfuric acid that they inject down the center well here in the yellow, and then it's recovered from the perimeter wells. Usually this requires an impermeable layer somewhere around it to keep it from getting into other basins and things like that. So a little bit about mineral resources, mineral reserves. Mineral resources have reasonable prospect of eventual economic extraction. So we can't call something a mineral resource unless you can demonstrate that it's potentially economic. So you can drill material, you can know how many tons you have, you know what the grade is, but if it's not economic, you can't call it a resource. And then mineral reserve then takes that part, and it's part of the mineral resource that can then be extracted economically. And I've got a figure here that shows, so on the left here, we have increasing levels of geological knowledge. You have your exploration results, which is just, it can be grab samples, it can be simple soil samples right off the surface. Then you get into start drilling holes. You increase the level from inferred to indicated to measured, which is your highest level of mineral resource. And then you can convert mineral resources to mineral reserves by applying the modifying factors. And the modifying factors mean you have a mining method, a processing method. You have the economics and marketing, legal, environmental. Everything else has to be in place to convert mineral resources to mineral reserves. And when you see a company has mineral reserves, that means they've done quite a bit of work. So it's a good market or good marker to determine whether a mining company might have something worth buying when they start stating they have reserves. Two things that affect mineral resource and mineral reserves are dilution and extraction. So dilution is the material you break that comes in that you don't really want, including the waste material, sometimes because you get overbreak. It includes where you don't recover the ore because you didn't break it hard enough. And it basically takes waste material and adds it to your ore and it dilutes it down. So that's the whole concept of dilution. Normal conditions expect 12 to 20% in underground mining, and in open pit mining, you normally see 5 to 10%. Now, dilution can be a big factor if it's a high grade property with waste rock that doesn't have grade, but it may not be such a problem if you have like a disseminated copper deposit that's, got copper all the way around it, but it's just lower grades on the fringes. And you still don't want that dilution, but you can get additional material coming in. And then you get dilution every time you rehandle material. Every time you pick it up, put it in the truck and dump it somewhere and pick it up again, you're going to get more dilution. Yeah. This shows an underground stope. So the blue is the original design that the engineer designs, lays out this rectangular shape and, picture perfect and all that stuff. And then you get overbreak and underbreak. So your overbreak, you're getting some waste material here in green. You got ore that's outside your block that you didn't recover because you didn't know it was there. That's shown in the black. And then, so you have to allow for all these other factors for dilution and extraction to account for what you're actually going to get out of the ground. So even though somebody says they have a resource, typically resources don't include dilution. That's one of the modifying factors. And when you add the modifying factors, then you have mineral reserves, and that means that they've already accounted for the dilution. And then extraction is basically what you recover, what you plan to recover. Did you get 95%? Did you get 98%? How much did you actually get of what you planned? You can get close to 100% in open pit mining because you're defining the shape pretty well, and you can mine to those pretty closely. But it can be 65% in some room and pillar mines because you got to leave the pillars behind. Normal conditions expect 85 to 95%. And then extraction is a trade-off with dilution. How much do you want to take of the waste and how much dilution are you willing to suffer? Talk a little bit about mineral processing. Basically, this is the separation of the ore material from the waste material. It requires crushing, fine grinding, and then you grind it down to the consistency of flour, right? It's like a mill. So you're milling the material, creating fines, and then the fines, once you have the fines, you can separate them. You can concentrate them. Typically, like in copper, what we do is we basically float it. It attaches to a bubble, and the copper will attach to the bubble and come to the surface. In gold, you dissolve it. The gold will dissolve in cyanide solution and go into a solution, and then we can recover it either on carbon or by putting zinc or something else in there to replace to take up the cyanide and drop the gold out. So there's flotation is one of the big methods for base metals, and then leaching solution electrowinning is common for precious metals like gold and silver. So fine grinding, this is a semi-autogenous mill. This is they're up to 40-foot diameter, 44-foot diameter nowadays. Some very large mills, and they call it semi-autogenous grinding because you use the big rocks to crush the little rocks. You feed big rocks in there to make sure you have some material, but as you're grinding it, the big rocks will crush the little rocks and basically save you some cost. But even then, a lot of people still add about 5% steel balls in there to keep it grinding, get the fine grind. So this has a sag mill here in the middle of the picture. On the other side there is a ball mill. So ball mills basically run with a large charge of steel balls. And they're typically 2.5-inch size diameter. They're grinding the material up and getting it to that fine, the fineness that you need, like I said, the consistency of flour, so that you can grind that material up and then get it to attach to the bubbles. So here's flotation cells. These are 600 cubic meter flotation cells. You can see a little bit of gray material there. That's where the bubbles are forming. This is a copper flotation. And that's where you basically, it attaches to the bubble comes to the top, you skim that material off, and that's your concentrate. That's what you end up selling. And this shows it a little bit better. You can see a wet concentrate here where the bubbles are. That's where the copper is all attached to those bubbles. That's what kind of gives it the gray color. And then this is the material once it's dried and stockpiled and then ready to ship. So concentrates vary by the metal and the grade of the concentrate. So it depends a lot on geology. Copper, typically you see the highest concentrate grades in bornites and some of the primary copper minerals. You see lower grades when you have other things influencing it. And typically copper concentrate grade runs between 20 and 38%, with probably an average around 28%. So when you see somebody selling copper concentrate, they're selling something that has 28% copper in the value. So if you have a ton, 28% of that is copper. Likewise for zinc, typically zinc concentrates run 50 to 60%. Lead concentrates run 50 to 65. Nickel concentrates are lower. Sometimes you get cobalt. Sometimes you get precious metals, platinum group metals. You'll get some platinum group metals a lot of times with cobalt or with nickel. In the concentrate, you get paid not only for the primary metal, but sometimes for secondary metals. In copper concentrate, you'll get paid for gold and silver. So you get a precious metal credit. And then there's penalty elements. So you don't want fluorine. You don't want other minerals in there that can affect the processing. You don't want something that creates either too much heat or not enough heat. So you got to have so much sulfur. So you got to balance all the material you're getting out and make sure it's a good clean concentrate that the smelters like. And sometimes you end up finding another mine that has a different problem with a different penalty element, and you blend the materials together so that you can get the right blend to feed to the smelters. Gold processing. So gold can dissolve in cyanide, so it dissolves in like a clear liquid. There's two ways to recover gold once it's in solution like that, and one is carbon. So same thing like the filter on your sink. If you ever seen the little carbon filters people put on their kitchen sinks to filter the water, it does the same thing. The carbon takes out the 2+ ions. So it'll take out iron, which is most people use it for at home, but it also takes out gold and silver. So the gold and silver will attach to the carbon, and then you can strip the carbon and produce the gold doré. And gold doré is gold and silver and some other metals typically combined, but it's a saleable product that you can then send to the refinery. The other method for precious metals uses zinc. As I mentioned, the zinc will go into the solution and the gold and silver will drop out because it's replacing the zinc in the cyanide solution. So refractory gold is one that has more sulfur, so it ends up being roasted first to basically oxidize it and to make it more amenable to leaching and the use of cyanide. So cyanide can be affected by carbon if you have organics in what you're mining. Say you have plant roots and things like that, it can screw up your recovery. It can also be messed up by other minerals that that like cyanide. So sulfur is a big problem for gold recovery, and that's why you end up roasting it. So heap leaching, this shows typical heap leach. It's just a pad out there. You put drip lines on the top. You drip a weak cyanide solution on the top. It takes the gold into solution. You recover it down at the bottom in a pond. You take that material and you process it. So just like some farmers and other people use with their drip irrigation lines, it's the same basic concept. So recovery is the percentage of metal that's recovered by processing and shipped. It's very dependent, as I mentioned, on the minerals. So as I mentioned, if you have a bornite or something that's typically got good recovery because of the mineral association, you can get up to 38% of copper into your concentrate. Gold, we normally see about 90% recovery from a processing plant. Heap leaching is typically lower. It's a lower cost, but it's also usually lower recovery. So if you have a high-grade gold deposit, you probably want finer grinding and getting more recovery. So typically you don't see heap leaching for high-grade gold. And silver can be the same way. Typically silver recoveries are lower than gold. Copper normal recovery is 87% or so for copper recovery. And then each metal and each deposit is different, but there's ranges here that if you understand the ranges, you understand what the people have when they state their reserves, you can understand pretty close to what some of the economics are of the project by understanding some of the recoveries and the what they're going to get paid for. So smelting and refining is when you take that product and you basically take it to the smelter. It's exposed to heat. So copper concentrates, as I mentioned, around about 28% on average. They send them to a smelter in Japan. They melt it down. They recover the copper. They also recover gold, some platinum group elements, and other minerals. In a gold circuit, when you're using a cyanide, you typically do a doré. It's usually looks like silver because there's more silver typically than there is gold. So it's kind of a shiny silver color, but you get paid. You send that to the mint, they'll separate it out, or Johnson Matthey, one of the refiners, and they'll separate the gold and silver, and they'll pay you like 93 to 96% on the value of the metal. So talk about a little bit about mine operations and cost. One of the key things, as I mentioned, is the geomechanics. How strong is the rock? How does it stand up? It's one of the key successes of any mine. This is a picture of Bingham Canyon in Salt Lake City there, where they had a failure about 10, 12 years ago. And the whole wall came in and buried a bunch of equipment down in the bottom of the pit. There was no people because they were tracking it. They have radar. They were tracking all the movement, and they pulled everybody out of the pit like the day before. But once it failed, it buried quite a bit of equipment that they weren't able to get out in time. So there's different ways of handling rock mechanics. Same thing as you see on highways. You can use cable bolting. You can use nets. You can use shotcrete. You got to look at your pit slope angles, and you want to maximize that angle to move the least amount of waste, but you still got to be safe. So you got to make sure you have the right angle on your pit slope walls. We mentioned dilution and extraction already. Some of the other things with geomechanics is the subsidence, like when we're talking about block caving, or sometimes when you do longwall mining underground, it's basically taking a seam of coal out, and that ground will collapse. So you have subsidence. You have backfill. A lot of times underground mines will use their tailings, which is the waste product coming out of the process plant, mix it with a paste and put it back underground and use it for the fill. And that's a good use of the fill material, putting it back underground. But you got to have the strength and you got to have the right material to be able to do that. And then tailings is the waste material that comes from the process plant, and it's typically put into an embankment. But all this requires, geotechnical engineers, all these design work that is required to design these facilities to make sure they're working properly. Talk a little bit about infrastructure. So access is a big issue, transportation, how do you get to site? Power, what's power going to cost you? You know, you got to generate power. It's usually like 25 cents a kilowatt hour versus, you know, if you here in Idaho, you can get off the grid for about 6 cents a kilowatt hour, which is a big advantage. And hydropower can be down to 2 cents per kilowatt hour, like in Quebec and some places like that. Water is a big deal. What we're seeing now is that most of the mines down in Chile now are basically using seawater, whether it's desalinated seawater or just seawater for processing. It's becoming quite the thing because there's such a shortage of water in the desert areas of Chile. So they're basically bringing water in from the sea. And then labor is always an issue. What we're seeing is more autonomous trucks and things like that in some of these higher elevations because it requires more people, or it actually requires less people, but you know, it's a cost for the people that you have to have at a mine site to operate everything that you want to minimize that. So do you have a camp? And some of these camps are, you know, 5,000-10,000 people. It's a lot of people in some of these camps. Do you fly in, fly out? You go up to the northern Arctic in Canada and places like that, and everything's fly in, fly out. So, and you know, it's actually interesting because some of the northern Canada camps have some of the best food of any camps I've ever been in, because you better keep the people happy. So it comes down to make sure your labor force is going to be happy with everything you're doing. And I won't this be a whole separate subject here, environmental and permitting, but going through the environmental impact statements, make sure you identify all the impacts, doing all the baseline work, the socioeconomic impacts, consulting with stakeholders, neighbors, things like that. And then looking at community agreements, trying to put money back into the community. Because a lot of times, even though mines pay a lot of taxes, that goes either to the state or the US government or whatever. And a lot of local people don't see that money. So you got to basically help the local people as well and invest the money in there. Operating cost for mines typically expressed as $1 per ton, including all the cost of the mine gate. Open pit mines, as we mentioned, $10 to $30 or higher, heavily dependent on the stripping ratio. Underground from $15 to $200 a ton. So key items here are location, the power, the water, the production rate, and the processing method. So when you move more tons, economies of scale, right? So you're going to have lower costs if you have larger excavation. Capital costs, some of these small mines in Nevada, some of these receive $50 to $150 million just to start up a mine. Mid-size open pit mine in Latin America is $500 million. And the large ones now we're seeing over $2 billion. I'm working on the Stibnite mine. It's $2.5 billion. This one right up by McCall. So it's a big project. In a lot of these countries, you have currency risk, increases in equipment costs with higher manufacturing costs. And then it's always impacted by steel and oil prices. So depending on where you hit the market when you're constructing, and then where you hit the market with your metal price, it makes a big difference in terms of how it gets financed. Net smelter return. So this is what you get paid for at the end. It's the value of everything expressed in dollars per ton. It's after all your costs for transport to the smelter, the treatment charges, everything else. It's basically the cash you get. And then you look at that, and rule of thumb is that needs to be 2 times what your operating cost is. So if it costs you $1 to make it, you better be getting $2 in your net smelter return. So that's just a general rule of thumb in mining, is that you better have ore that pays pretty well to make it worthwhile. So talking a little bit about mining stages, I'll try to go through this pretty quick. I got a few minutes here. Basically, you go from exploration, advanced exploration, into different studies. Scoping studies, your first set of studies, pre-feasibility, feasibility. From that, you go into project financing, construction, startup, operation. So right now, I'm working on project financing for Stibnite. They expect to start construction in the spring, and startup will be in 2028 if everything goes right. So just kind of give you a feel for that. The mining life cycle takes many years to get to production. From your first discovery, it might take 20 years to even find a discovery. Just walking the ground and taking samples and things. It might take a while just to find something that makes sense, and then to go out in there and drill it some more and then prove it up. So this is actually a cash flow line that shows the money you're putting out as you advance the project through the studies and then into construction. And then you only make money when it's in operation. And then after operation, you lose the money too for the closure costs and things like that, the money you're spending at the end. So preliminary scoping study is normally plus or minus 35% accuracy. They typically cost between $100,000 and $750,000. It's used to help guide the project as to the next step and where they want to go. It uses inferred mineral resources, which is one of the lowest classifications of mineral resources. And you just do an initial cash flow and try to make sure it makes sense to continue drilling. Pre-feasibility is the first time you can actually report mineral reserves. It requires more engineering study, typically costs about $1 million or more. And then the feasibility study, rule of thumb is that this costs somewhere about 1 to 5% of the total project capital. Accuracy is supposed to be in the 10 to 15% range. You basically analyzed a lot more things. You know your geomechanics, you know your design, your life of mine plan. You've got full costing and everything else. And then project financing, you've got your studies completed. You've got a good mine plan. You've got something that makes sense in terms of cash flow, and you can present it to the banks, and the banks will help finance it. Typically for financing, we see about 70% come from the lenders and 30% equity from the sponsors. Construction, most of these mines the large mines take 3-4 years to build. You see crews up there, construction crews of 10,000 people, big groups. The EPCM right now for Stibnite is Hatch out of Toronto, and they're doing the EPCM work right now, getting things ready up there. You have to have all your design done. You have project controls. You have schedule and budget that you have to then track back against. And I know some of you construction management guys must know this stuff, but there's lots of jobs out there in mining on construction management side as well. Startup, which is oftentimes overlooked. Everybody thinks, oh, you flick the switch and it starts right up. Well, it doesn't. You got to ramp up and allow time for that to start up. This is called a McNulty curve. On top is a typical concentrator, like copper, simple process. It takes about a year to get up to full production in a typical copper mine. And then some of these other ones never reach design production because the technology hadn't been that well proven. So on the operating side, you have your planning cycles. You have to do your annual mine plans, things like that. Monthly reports, reconciliation. You want to go back and check your resource and reserves, make sure they're reconciling, and benchmarking against other operations to make sure you're keeping your costs in line. So this is the stage of project development. Basically, this is a value curve, the green line, showing as you have more information, the value of the mine goes up. And only when you get into production do you actually start making big money. But the value of the stock of these companies will increase as they advance these studies and start reporting mineral reserves. And this shows the development of mineral reserves up on top, going from resources to reserves. It shows the different valuation approaches that are used. You use the cost approach if you only have drill holes and no mineral resources. But there's different approaches to use for different types of properties when you're valuing them. And then closure, it's the last phase of the mining cycle. It involves shutdown and decommissioning, dismantling equipment, removing it, and then making sure you can return the land back to some useful, so it's useful for people coming through there later. Mining success is directly related to people. Right now, there's a lack of skilled people at all levels in the mining industry. We have generalists versus specialists. the generalists are good guys that know how to get things done, and the specialists are the guys you call in when you need help. So that's the way to look at that. And then precision versus accuracy, some people are more optimistic about how well something's going to go. Some people are more pessimistic. You really want to be in the middle somewhere, but it's tough to tell people that. And it's interesting to look at a project and see some of the different things they've done when you've looked at a lot of different projects, and help them understand where they need to make some changes. So there's a lot of opportunities out there on mining, certainly mining engineers, geologists, metallurgists, accounting, bookkeeping, all these people are needed, chemical engineers, somebody to run the labs, do all the analysis, mechanical engineers, maintenance guys, mechanics themselves, equipment operators, geological engineers. This is the geomechanics side. The civil engineers, the rock mechanics, people who look at the rocks and determine their strength, hydrogeologists or geohydrologists, whatever they like to call themselves. And, all these people are critical to the success of a mine. Safety specialists, construction managers, autonomous haulage systems, drones and surveyors, and people who run the equipment like that. Right now on autonomous haulage systems, it's actually, I just saw something for Waymo. They have a control panel where they have a guy that runs 6 or 7 Waymos at a time. And the same thing in autonomous haulage systems is that you have a control center, say in Santiago, and the guy's operating 6 of the trucks at the mine site, which is 1,000 miles away. So it's pretty interesting. And that's all I had. So, Doctor, try to keep it under 40 minutes. Not quite.
Well, thank you. And we got quite an impression of what a flavor it is to get into the mining industry, what kind of projects these are. While we give our speaker a little bit of time to rest, we will move on here in the room with some discussions. You might talk about these questions that we have in here, or you might also go from the impressions that you had, that we just have seen, pictures and questions that you have from that. Figure it out in your teams. All right. So thank you for starting to talk in your groups. That's awesome. And now we'll have the opportunity to interact with our speaker. We will, if you, Richard, would go into the 4th aisle and run there so that we can pass by the mic. So we have only one mic, and this time we will not have our speaker repeat the questions, but Mr. Lambert will have the opportunity to just get the phone from you, and we pass it back and forth. So we'll do a little bit of a relay in this room in here. And the first question is already back there.
So usually engineers are pretty safe when it comes to their estimates. So why you mentioned in the ramp up phase, how is it possible that their estimates come so short, as far as you said that sometimes you never actually get to full production for your ramp up phase? How can that, or is it because that the engineers are a little more lax on this? Because I feel like usually they give a lot of room for that not to happen. And then when that does happen, does that cause a risk to the whole entire project as far as profitability, or do you think about these things in that long lead up time?
So good point. Typically, most engineers build in a factor of safety, right? And that's what you want to do. But the problem is technology, and what you can do in the lab sometimes in recovering metals, say cobalt, can be tricky, especially, let's take, for example, rare earths. So rare earths, to separate rare earths requires different resins to basically separate, and they collect to, and different rare earths collect to different resins. So it's all that technology and how you get that up to scale. So they can prove it in the lab, but it's getting up to scale and being able to make it productive. And it's usually the more technologically challenged ones are more the rare metals and things like that. But like copper and gold, most of those plants are pretty well designed and will be on that Series 1 curve on the top, with usually full production within a year.
So you've got a cue. Smell it.
You were saying that the construction process is like a super major and long process for a mine, but what are they actually building? Like I'm struggling to figure out what they're actually building, I guess.
Most of the construction is tied to the process plant. So the mills and things like that. And maybe we can show you on the picture here. Some of these big mills like this, you wouldn't, it's got 30 feet of concrete underneath it to support that. You're in higher earthquake zones and things like that. It's amazing the amount of work that goes into these, not only in earthwork, concrete, steel, everything. And it's designing those buildings and things that really takes a big challenge. It's a big challenge, and then scheduling it and make sure everything gets done in time. So, I mean, the thing we typically see is earthworks is pretty simple stuff. Most people can do civil things pretty easily, but it's right at the beginning of the schedule. And it's one of the few things that when you underestimate earthworks, it's a problem because it screws up the rest of your schedule.
Hi. So, in comparison with other places you've worked, like Chile and in parts of Canada, where would you say the United States is lacking in its mining industry, and where would you say we might be ahead of the curve?
I guess the big one there is on the permitting side. Usually, it can take 10 years to permit a mine in the United States, and that's typically been a problem for a lot of projects. And it's not. Sometimes it changes in politics and different administrations. The current administration seems to be more favorable, but it varies, and it varies by country. They actually rank these. There's a group out of Quebec that ranks all the different mining communities in the world, and like Quebec is number one, and Australia is very high up there. Nevada is actually pretty high up there. Chile, places like that. Some of the bigger mining communities have some of the better permitting and better curves for construction.
I thought it was interesting when you talked about the ethical issues with giving back to the actual community that you're taking the minerals from. And now, is there a standard across the board that you have to give like a certain amount back, or is that based on the company you work with? How do they come up with that? And is that why the environmental or the permitting process is so long and there are negotiations that are taking place?
I don't know that that actually adds to the time, but the key thing is that you have to involve the local communities. And like I said, a lot of the problem there is taxes is what you're paying a lot of taxes and you're hoping the money goes back to the community, but it doesn't. If the state's collecting taxes, it comes to Boise first, right? And that's, how things work. And the same thing with federal taxes go back to DC and how much you're going to see back in Idaho. So it's key to work with the communities. And there's actually a thing called the Equator Principles, which is a set of principles around mining and things like that, that basically designates these things. And they have to be addressed for the major banks to lend money to these companies. And so each of these Equator Principles addresses stakeholder value and things like that and make sure that people are addressing them correctly. So it helps when you have financing because it puts another layer in there of make sure things are get done.
John is the next over here.
You made the list, John. I think there's someone else. Okay.
So there's a lot of debate about whether or not the AI boom right now is a bubble or not. How much of, if say it was a bubble and that bubble was to pop, how much of the I guess infrastructure wouldn't be that recent, but how much reliance on this new boom for minerals critical to AI are these mines like dependent on, or what would happen if it was to pop?
I don't know that, right now, basically the only minerals we're getting is what we're already mining, right? So it's not really reacting to the AI boom. What affects that is price. The metal price will go up because the demand is high and the supply is short. So we're seeing a big boom right now in all the metals. Copper's over $6 a pound when it typically was hovering around 2.5. Gold's over 5,000 an ounce. Silver's $120 an ounce, whatever now. I struggled when I was at Delamar trying to get $5 an ounce. So, the metal cycle, it goes up and down. But I think you hit a new step each time. And right now we're seeing that copper is very important for infrastructure and for circuitry and things like that. We don't have enough copper, and we won't have enough copper in the next 20 years. So it's just going to increase the price, I think. It's supply and demand is what it comes back to, is what price you're going to end up paying for the metals and what substitutes can you find then to do the same thing. So a lot of time, remember back in the days on electricity, they used to run a lot of aluminum cable because it was cheaper. You might see something like that again because copper prices are getting pretty high.
Your instructors will be practicing putting out fires slightly later this semester. We get the bucket brigade going here.
So you had an example. You had an example about an operator in Santiago just running the machines down in a mine 1,000 miles away. I was curious if there are any exciting technologies that you are looking forward, and what are some potential things that you think would greatly help the mining community, where it's, drones or just electric tractors. I don't know. Just what do you think is missing?
Probably easiest just to tell you what I see currently and what some of the changes we're seeing. So certainly autonomous haul trucks are a very big thing. Certainly GPS, and right now they're putting in all the wireless communications into the open pit mines so they can communicate anywhere around. So they're not just relying on GPS. They have their own network there. One of the interesting things is underground mining, RFID chips. So I can wear an RFID chip on my person. That's my tag when I'm underground. And if I walk up to a piece of equipment, it will turn it off. So safety is a big deal. And you're seeing a lot of technology there to make things safer and, basically keep people from getting run over when they're in the wrong place. And I think there's tons of things like that we'll see more of in the future. That's just a couple of examples I can think of now.
You had a quick slide about closing costs or closure. I was wondering what percentage of the budget of a mine that usually takes up.
So this is an interesting one. It depends on where you're at, but what we typically like to see is that the project funds closure from the beginning, so that each ton of material moved, each acre of disturbance has coverage. We see it now in most all the U.S., Canada, Chile, all these places now have requirements for posting bonds and for allowing for that impact. And so what there is it's money is set aside as you're mining, put into a capital account that basically reserves those funds for reclamation and closure. Typical closure costs on a small mine, maybe like this one here, might be 20, $30 million. Some of the ones down in Chile, we're seeing $200, $300 million being allocated for closure costs. So it varies depending on the mine size and the footprint, and then just the entire environment. Because Chile, a lot of these mines are in the middle of the desert, so I mean the impacts are small because there's no water. But again, it's where you're at and the costs all need to be accounted for. It's as I mentioned, it's also in the equator principles, the closure costs, and making sure that's fully funded from the beginning.
So you mentioned bond, like they're requiring bonding. So in like especially in like the $20-30 million bond costs, are you struggling to find companies, especially for like a $2 billion project, to be able to actually be like, yeah, we'll cover, or are you struggling to find companies that will put up the protection for these costs? This is my question. Yeah, have the bonding capacity.
So a couple different things there. First of all, the $2 billion is the construction cost, not the closure cost. So the bonding is primarily for the closure cost. Construction bonds are a whole nother thing, and it varies by the market and who's had accidents lately, how much it costs for construction bonds. But on the closure cost side, there's people that are willing to fund those things and put up the bonds, and reliable, AAA type bonds. So.
And then we're coming back to that. You got another one?
No, I thought.
All right, okay.
So in a book we're reading for class, there was a chapter about Rhyolite Ridge, the lithium mine by Reno, and there was discussion about there was a flower there unique to that area. It was exclusively in that area, and in 2020 it disappeared completely. And I was wondering what sort of discussions mining executives, or mining employees have regarding the biodiversity effects on a prospective mining area.
That's a good question. So again, this is one of the things that's covered under the equator principles. Biodiversity is. I'll give you an example. So I worked at Quebrada Blanca mine down in Chile, and they were putting in a pipeline, and they have a plant there that was protected. It rained, and all these plants pop up. Nobody knew they were there. Thousands of them, and it wasn't quite as rare as they thought it was, but they ended up having to fence the entire area off and go around the area to protect the plants. And you'll see that with most operations. So, and it's not just plants, it's animals. And I mean, we've got the same project has a lizard down there that pretty rare and not seeing many of them. And they actually put in a program to have these lizards mate and create more lizards. So they're doing things to not only recover any impacts, but also to basically make it grow. So.
Here in the front.
As far as like the open pit mines and stuff, are you guys just trying to fill those in, or are like what is a part of the closure process for an open pit mine? Like, I guess filling it in, or just kind of leaving it and letting nature kind of reclaim it? What is the typical process?
That'll vary by state and by different areas, but typically you'd like to see it put back to productive use. It's, BLM and some of the federal lands require that you put it back to some kind of use, whether it's grazing or something like that. So we see a lot where they do cattle grazing or something like in Arizona and things like that. And actually the cattle actually help the reclamation process because they cover everything. But like this picture here is a pit, and they left behind a lake, and the water's nice and clean, which is one of the issues with pit lakes. We have one up in Butte. It's a Superfund site. because there's a lot of copper in the water. So there's still trying to figure that one out. But that's all part of the closure plan. And if that had been done ahead of time, they would have had a plan to deal with that. Hopefully everything's covered in the closure plan. The agencies responsible for that should have looked at that.
Great. You said there's not going to be enough copper in the near future due to the big boom, like with the trend that's going on with AI and data centers, that it's going to be possibly that they're not going to be able to supply enough with everything that's happening right now. Do you think that mining will increase production because of that, or will it not shift and stay the same while prices continue to increase until like a point is met where a big consequence happens where something has to be kind of sacrificed, where maybe production of AI stops, or they have to kind of do what you said earlier, aluminum's back into wiring? Is that what's going to be happening, or will mining continue to increase for that?
So it all comes back to supply and demand. But what you'll see, first of all, is if there's a shortage, prices will go up, and they'll look at substitution aluminum. But longer term, they'll try to increase production as much as they can. The thing about prices is going to drive them to mine lower grades. So it's more processing that you have to do to get more copper. So it's gonna, I mean, you're not gonna see copper double in the next 10 years, even though it may need to. It may take 20, 30 years to see that kind of growth. It's not gonna, the thing is that all the good deposits have been found pretty much, right? So the other thing about mining that's always interesting is that it's an asset that you have that you can't see. So unlike a building, and you know that building's worth $20 million, this material in the ground, you say it's worth $100 million. You can't see it. How do you know it's worth $100 million? And that's where the drilling comes in and other things like that. But it's one of the few assets you can't see.
I had a question on the cyanide dripping solution that you talked about, and wondering if there was any like issues that you've seen so far with runoff from that.
Not with runoff. The thing with cyanide is it breaks down pretty easy into carbon and nitrogen. In fact, you know, they used to use it kind of as a fertilizer and kill rodents and things on farms, and it would break down naturally into fertilizer, essentially. The thing about cyanide is it degrades with sunlight. It also degrades just with the atmosphere and oxygen and anything that exposes it. It's got a pretty short life, actually. And the solution you're using is very weak cyanide solution. Like some of the ponds and things that you have in a heap leach, a lot of them are netted and things like that, protect birds and things like that. So the higher concentration areas are covered, and you try to protect. I mean, it's just common sense. And working around any chemicals, you need to make sure you're aware of all the hazards of it. One of the ones that we actually use a lot of in the mining industry is hydrogen peroxide. Hydrogen peroxide is great for killing cyanide. But hydrogen peroxide, you get 70% hydrogen peroxide, you drop it on a leather boot and can catch fire. So a lot of people they think, oh, hydrogen peroxide, I use that for my hair. But yeah, there's different things with different chemicals and things like that, and you need to be aware of that.
Yeah, room maybe for one question, maybe for one from online. Is anything remote? If anybody wants to unmute remotely and just speak up. That seems not the case. So we had a lot of questions. Thank you very much all for participating in this. And with that, let's give another round of applause for Richard Lambert.